Good day, welcome back. Joe Cooper-Sandin here. This is Blackboard Video 4D. We're going to move away from measures of position and we're going to move into measures of spread. Very important lesson here, describing the spread. We know the center, means and medians. We learned about measures of position, quartiles and percentiles, and those are certainly important. But in my opinion, even more important is how can I characterize how much spread there is in a distribution. I have a histogram here. I found some data on the internet. These are Albuquerque home prices for homes that recently sold. And of course this is skewed to the right, and we would use the median to describe the center. If I'm eyeballing it, somewhere in here is the median. It would put half and half of the data to the left and to the right of that red line. And that's important. Maybe it's 110,000 or 100,000, somewhere in there. But it's a completely different picture. If home values are, say, 80,000, 90,000, 110, 130, that's very different than if home values go from, say, 50,000 up to 600,000, right? And so we need to start to characterize how much spread there is in a data set. Okay, so that's the main point of this lesson here. We'll start with the easiest measure of spread. It's the range. All I take is the maximum value. I subtract off the minimum value, and that's it. It's very limited in its usefulness. If I have a large outlier and a small outlier, the range will be take the distance between the two. Okay. How many data values are we using? We're using 2. In the Albuquerque home values data sets, there were over 100 homes, and I'm throwing out almost every single one of them to try to characterize the spread. Okay. If you're ever asked, students, to describe the spread, don't use the range. We can do better than the range, and so let's do better. Next one, interquartile range. Previous lesson we learned about quartiles. Now let's use those to come up with a measure of spread. This is almost always abbreviated IQR, typically all capital letters. So if you see IQR, you know what that means. It means interquartile range. Here's what we do. How spread out is the middle 50% of the data? So if here's your data set, I get rid of the top half or the top quarter of the data and I go here. I get rid of the bottom quarter of the data, I go here, and I take how much spread is there in this middle 50%. Okay? We have to get the quartiles first, right? Q1 and Q3. And once we get those quartiles, we'll just find the difference between those. We'll look at the range between the two quartiles. Okay? So there's a very easy formula to get IQR. I don't do max minus min. I do third quartile Q3, and I subtract off first quartile Q1. This is better than the range. Okay? If I have some outliers, IQR won't be really affected by it because I'm just looking at the quartiles. We're still throwing out some data, so we need to be aware of that. We're really only using 2 values to characterize the spread with IQR. The idea is this. If your data values are very spread out, then the middle half of them should be very spread out, and IQR will get big. If your data values are very compact, very tight to the center, then the quartiles will be close together and IQR will be small. Okay? I guess you could go to this extreme. The smallest IQR could get would be 0, right? If all of your data values in the middle of your data set were the same value, IQR could be as small as 0. This is rare. I mean, I'm not saying this is going to happen every time you have a data set. It could be as small as 0. And I suppose there's no limit in terms of how big this could get. If your data values just have a ton of dispersion, a huge spread, then this will get very large. Okay? It can't be negative, by the way. I should probably write that down. This can't be negative. If you calculate it by hand and you get a negative number, I would say maybe switch the order of these and try again. All right, let me advance the slide. Quickly, we'll visualize the range in IQR. Albuquerque. I have a histogram, so I'm not sure if the lowest priced home was exactly $50,000. It was somewhere here between $50,000 and $75,000. But the range essentially goes from about $50,000 up to $225,000. Remember, the range is just one number. I would take max minus min. And this will be approximately $225,000 minus on the low end, $50,000. If I had to eyeball it, range would be about $175,000. Visualize the IQR. A little bit trickier. Somewhere in here is the bottom 25%. Hard to be super precise with just a graph. Somewhere up here is the top 25% of the data. And what IQR does is it says how much spread is there between the middle, 50%. I'll take the easy numbers just because my lines are close. Again, this is an eyeball job, but Q3 looks like it's about 125,000. Q1 looks like it's about 75,000. So if I had to eyeball IQR, approximately Q3 minus Q1, approximately 125,000 minus approximately 75,000. So best guess, ballpark, roughly 50,000. I'll put 50K, just sort of ran out of space there. Okay. Again, that could be as small as 0 if there's not much spread, and it could blow up. Could never be negative. All right, let's calculate one for real with data. Calculate range in IQR for the cycling data. We've already calculated the quartiles. Let me just pop them in. Here was Q2, or the median, and we've already done it a few times. That value is 189. Q1, I go to the bottom half of the data, just happens to be on the top row. 180 sits right at Q1. 205 sits right at Q3. I'll go quickly because we did calculate those in a previous video. Calculate the range. Take the biggest value, it's 244. Subtract off the smallest, it is 160. And looks like it's about 84. IQR, we're taking the range of the center 50%, Q3 minus Q1. Remember, the bigger number comes first. It's 205. I subtract off Q1, which was 180, and that is 25. I'm reminding myself down here, how small can IQR get? We've answered that question. 0, right? It's the smallest it can be. Okay. Again, if you're asked to pick the best measure of spread, let's not pick the range. We'll do IQR, or possibly even better. Let's move towards better. For any distribution, I'm talking shapes, symmetric, skewed, outliers, IQR is certainly reasonable, but it does have some drawbacks. For one, aren't we discarding the bottom 25% and the top 25%? Not terribly crazy about that idea. IQR is best for data that's skewed. So again, just like when we're looking at describing the center, we have to go back to graphs. You have to know what the shape is telling us, and then we start picking the best statistics to describe what we're seeing. If there are a few outliers, IQR won't be affected, and that's why we pick it. Okay? For skewed data, students have a little bit of trouble with this. Let's get this right. For skewed data, if I'm describing the center, I pick the median. for skewed data to describe the spread, right? For skewed data, use the median to describe the center and use IQR to describe the spread. Median, IQR. Those go together. They're like a married couple. Okay, so remember that, students. And that's for skewed data. Sort of know the answer to this next one, right? If the data is symmetric, we're going to do better than IQR. For symmetric data, we'll use the mean. To describe the center, we'll use standard deviation. We've encountered standard deviation before. Now is where we formally define it. Symmetric, mean to describe the center, standard deviation to describe the spread. Top level, why would we do that? Symmetric data typically do not have outliers piled up at one end. That's where we run into problems, right? Skewed will. Outliers distort the mean. If I have high outliers, pulls it up. If I have low outliers, pulls it down. And what happens is it inflates the standard deviation. So outliers distort the mean and inflate the standard deviation. Big outliers will crank up that standard deviation, and it won't be the best measure of spread. All right, let's define standard deviation in words. We'll get the formula up, and we will call this lesson over. Common language definition. You've probably heard this in class. Standard deviation is I'll put it in quotes because it's not precisely, but it's like the average or typical distance to the mean. Standard deviation is like the average. If you like typical, I'll put typical. Distance to the mean. Remember this, it's important. Standard deviation, one of the most important concepts in Math 127. Here's your data points. Here's the mean, and on average, how far are my data points away from the mean? If my points are close, standard deviation will be small. If my points are very spread out, standard deviation will be large. And it's like that typical distance to the mean. All right, we've got to get that formula down to wrap up. I'm going to put it on the sideboard here. Let me get a data set just to refer to it. This is the cycling data. Okay, and we're familiar with this. We're not going to calculate it in this video. We'll save that for next time. But over on the side here, let's get the formula down. Symbol we'll use in this class when we're working with the data is just S for standard deviation. And let's think of the verbal definition. It's like the average distance to the mean. When I think of an average, I'm thinking I have to add something up and divide it by how many I have. So let me put the divided out bar there first. And standard deviation. It's like the average distance to the mean. Think about the distance, okay? If I look at my data, I will call these my y values. Typically in this class, we'll use the letter y, and for the cycling data, I have about 14 of them. And we know the symbol for mean, right? We know the mean, that symbol is y bar. So I have to start calculating distances. Here's how I do it. I take my y value and I just subtract off the mean, y bar. Okay? This will give me the distance. I sort of cycle through every one of them. If I was going to calculate this by hand, I would start with 160 and I would subtract off the mean. Y minus y bar. I would go to the next data value. I would go to 174. I would subtract off always the mean. And I would have to go through all 14 of them because I need to see how each of those cycling leg strengths relate to the mean. So it's always y minus y bar. Okay? It's like the average. Average tells me I need to add it up. So up top, here's our added up symbol. That's that summation sign. So this is saying sum up all of the distances to the mean. Average it out. Well, I need to divide by how many that I have. How many do I have for the cycling data? There were 14 data points, so we know n needs to show up down here in the denominator. For more of a technical reason than anything, it's not exactly n. What we need to put down here is n minus 1. And so if you go back to the verbal definition of standard deviation, we said, that's sort of like the average distance. Here's that like part. Okay? Now, if I did this for any data set, what we need to realize is we're going to run into a problem if I left the formula as it is. If I take 160 and I subtract off the mean, I'm going to get a negative number. If I move to 174 and I subtract off the mean, I'm going to get a negative number. All the values that are below the mean, I'll get negative numbers. That would be helpful if we knew exactly what the mean was. So I'm going to grab that number, and we calculated this a few lessons ago just so we can see this on the video. The mean of the cycling data was 192. So what you can see is if I take a 160 and I subtract off the mean, this value is below the mean, I'll get a negative. The 174 is below the mean, I'll get a negative. As I'm adding up those distances, negative, 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 bunch of negatives, negative, negative, negative. Well, finally when I get to some of the cycling data that's above the mean, I would start to get positives. 194 minus a 192 will give me a positive number. And so, bunch of negatives, add to it a bunch of positives. We run into a problem, and the problem is that this will always add up to 0. For any data set, if I just did this, take all the distances, subtract off the mean, average it out, I get 0 every single time. So we have to fix the problem. And here's the technique that we'll use to fix the problem. If I square negative numbers, what happens to a negative times a negative? Becomes positive. So, we're bending the rules really with this average. We said standard deviation is like the average distance to the mean. And you can see why. We're not quite dividing by n. We're going to square things out. If I square the distances, I'll get positive numbers. If I leave my formula like this, we're almost done, I promise. I will have my s is going to be in squared units, and I don't want to work in squared units. I want to get back to, say, cycling data, whatever units that the cycling data is in. So if I square up here before I average them out, what I'll need to do to finish this up is unsquare it. So we'll square root. It's not the world's most complicated formula, but we hope we can see exactly why this works. I take the distances from the mean, I sort of average them out. This will always add up to 0, so I square to get rid of the negatives, average it out, and I wrap up by unsquaring. Okay. So we finish with this in this lesson, and when we come back next time, we'll actually take the cycling data and apply the formula. And you'll see that it makes sense, and we'll be feeling real good about it. All right, thanks.